Yeah, so can you tell me one deficiency of Hartree-Fock theory, even though it may recover 97 to 98% of the total energy? Because you already have been taught Hartree-Fock, and I think the deficiencies also. Any one of you? Hello? Yeah, I'm surprised. Doipan, you're on the screen. Can you tell me what do you think?
Sir, I am not sure.
You are not sure why 97, 98% is not good. All right. But do you know any other deficiency of Hartree-Fock? Restricted Hartree-Fock in particular? Is the dissociation problem is not taught? Hydrogen molecule to H plus H does not come out well.
I think no, sir.
Huh? No?
I think no. I have missed one class, but I am in other class. I think it has not taught.
Okay, that's surprising. So what has been taught? The entire algorithm has been taught?
Yes, sir. The algorithm.
After that, what has been taught? The charge density bond order matrix has been introduced?
Charge density was taught, then population number was taught,
population
and then moved into the basis sets.
Okay, that is fine. That's a part of the Hartree-Fock. After that?
Basis, after completion the basis set, taught one class on unrestricted Hartree-Fock.
Okay. All right. Yeah. So we will see. So let me share the screen now.
Sir, actually, that deficiencies are not taught in that much detail.
Okay.
Actually,
No problem. So let me start and first ask you a very basic question. So Hartree-Fock theory is deficiency. So I'm asking a question now because we are going to improve the Hartree-Fock theory. So the reason I'm teaching you this is that I must first know why do I need to improve. So for most systems, particularly which are closed shell, I hope all of you know what is closed shell. What is closed shell system? Tell me. Can somebody define what is a closed shell system?
all orbitals are filled.
Okay. All special orbitals are doubly occupied.
Yes.
Correct. So I will define the closed shell system. But for most closed shell system, the restricted Hartree-Fock gives you 97 to 98%. I mean, it of course is not exact. It may be 95 the total energy, at least for ground state. Okay. So normally a physicist will ask you this question and you have to answer that why do you people go beyond Hartree-Fock, which is a very nice model. It has a one electron in one spin orbital. So it's a very nice model, right? So why do you want to improve? And this, so they think that the quantum chemists are splitting hairs. You understand what I mean by split hairs? They are working in the digits and they are not important. They feel because you are only now the rest of the course will be all this 2 to 3% improvement. So can you answer that first immediate answer? I think one of you or two of you are in physics, right? So when you go back, and that's something, there is a difference between physics and chemistry. Can you first answer this question? Any of you? I'm sure this has been told at some point. No. Is somebody taking my evening class on DFT? Hello? Even there I have mentioned in the very first class. You know, I don't know, those who are chemistry students must be knowing that I am taking a DFT class. Very awareness class, of course. Not very great detailed theory. In the evening, today there is 8 o'clock, there is a lecture, 8 p.m. Do you know it? Hello?
Can you please repeat the question once?
No. I mean, do you know that I'm taking a class of DFT in the evening?
No, sir. We are. I am physics from
Oh, you're a
physics.
physics student. But chemistry students, do they know? Is it informed to the BSMS students or only to...
Yes, sir.
You know? So even in that class, I have discussed this, why it is not important. So today there is 8 p.m. there is a class on DFT. So it's awareness class. So if you are interested, you can join. Sumanda Sarkar from chemistry is organizing this as a seminar secretary. You can get, or any of your friends will give you the link in Zoom. Okay. All right. So we discussed this. So let me first tell you that in most of the chemistry, what we are interested is never the total energy. But what we are interested is difference of energies. So I will give you examples how. So difference of energy. So for example, you are interested in how much energy is required to ionize a system. Right? So what is this? This is nothing but electron for the n-1 electron system minus the electron of the n electron system. Is it not? So this is called vertical ionization. So at the same geometry of the atoms, I take out the cation, I take the neutral system, subtract, right? I hope all of you know this, the definition of ionization, right? Then I do similarly electron affinity. Please make certain comments, yes or no, because otherwise I get confused. In a physical class, I can see all of you. Here I am not able to see. So that is the reason I am asking. So for electron affinity, for example, you calculate this quantity, En minus En plus 1. Right? Yes.
Sir, what the ionization potential is for vertical ionization?
Yes. I have written here. Vertical ionization. So vertical ionization and adiabatic ionization only differs in the geometry, but the basic idea will remain the same. This minus this. Only thing is that this will be calculated at its own geometry, the cationic geometry. So that will become adiabatic ionization. Geometry is frozen. But the point is that both ionization and electron affinity are excited states. What is an excited state energy? It is also one En of the excited state star, let's say, minus En of ground state. Okay, then let's say I have interaction energy between A plus B going to some, let's say, AB or C, whatever. So what will be the interaction energy? This will be also EA plus EB minus EAB, right? I have made it deliberately look like such that if AB is stable, then the interaction energy is positive. So you have to always write A plus B minus AB. Many people write AB minus A minus B, but then it will become negative. That's all. So this is the interaction energy. Please tell me if you don't understand. Anything. If you do geometry optimization, so that is comparing energy at two different geometries, right? And then finding out which is minimum. So in a way, this is also difference energy. Now, if you look at some of these common problems, so interaction energy or binding energy, like binding energy is hydrogen or fluorine plus fluorine going to F2. So it is again the difference. So just like the interaction energy. So if you look at hydrogen bond, it's also difference energy. If you look at all the problems of interest, they are all related to difference of two energies and not the energy per se. We are really not interested in En per se. We are interested in En at a equilibrium geometry compared to the other geometries. That's optimization. So that is in a way the difference, right? So everything that in chemistry we are interested is actually a difference of energies. Unfortunately, the total energies are very large. Whereas this difference energy is very, very small. For example, if you have one system and another system and you are just looking at weak interaction, this is a very common problem in chemistry. These interactions are of the order of, let's say, 10 kilojoules per mole. Whereas these systems are few atomic units, 100, 1000 atomic units. So you know, one atomic unit to kilojoules is more than 1000. Right? So this can be few tens of thousands kilojoule. This can be few tens of thousands kilojoule, and you are taking a difference which is 10 kilojoule. You want this number to be accurate. You understand? So if I'm taking a difference of two large numbers to predict a small number, what do I want? I want that these must be as accurate as possible. Correct? And this error bar of 2 to 3% that I have is much larger than this difference energy. So you can easily have 100 kilojoules error. And then you are saying 10 kilojoules is in Hartree-Fock, and 10 kilojoules is a very predictable number. Nobody will believe it. Right? So the difference energies are much smaller compared to the error in individual energies of the RHF. So 2 to 3% is too large because this is much smaller. Is it clear? Hello?
No, sir. Can you tell me, sir?
Yeah, so the error bar of 2 to 3% is much larger than this difference energy that I'm predicting. So let's say I have a 1 million kilojoules. Okay? I have got in Hartree-Fock. Another system which I'm subtracting, okay, this is the subtraction of the whole system minus sum of the two, right? So let's say the whole system is 1 million, and in the Hartree-Fock you predict the other system is almost the same. Something like this. If you take the difference of these two, you get 10 kilojoules, right? These are in kilojoules. This is what you predicted, knowing that each of these has a 2 to 3% error. So you can imagine the error here. What is 1%? That will be 10,000 kilojoules. 2% is 20,000 kilojoules is error. Error means what? It can be that much less. Assuming that that much more, assuming that the Hartree-Fock is always higher energy than the exact energy. So this can be 3% higher, this can be 2% higher. Like we don't know how much. The error bars are not exactly same, right? So then this 10 kilojoules become meaningless. You may actually get by Hartree-Fock 100 kilojoules, 200 kilojoules, when the result is actually 10 kilojoules. So if you are predicting a number which is that small, then your original numbers from which you are taking the difference must be as accurate as possible. Is it clear? How much accurate? Maybe 0.1%, 0.01%, because that is what 10 kilojoules will be. 1% itself is 10,000. 0.1% itself is 1,000. So you can imagine, even that is not allowed. Hoping for an error cancellation, there will be some error cancellation. Typically 0.01%. And as large a system is, it's very, very hard to achieve this error. And RHF is pretty bad. So what I'm trying to say is that the 2 to 3% error that you are keeping in the restricted Hartree-Fock is not acceptable, because the energies of interest are not the total energies, but the difference energies, which are much, much smaller compared to the error bar. So I need much more accurate theory. Is it clear?
Yes.
Hello? Yes? Is it clear to all? That is the reason the chemist cannot believe in Hartree-Fock. So today, if you do any calculation with restricted Hartree-Fock, you cannot publish. So having learned all this, you cannot publish. But then if you do not learn restricted Hartree-Fock or Hartree-Fock, you cannot learn other quantum chemistry theories. So it is very, very important to learn. And that is the problem. So we spend a lot of time in learning Hartree-Fock, but by Hartree-Fock itself, you can do nothing. Okay? So we need much more accurate theory. The difference of the total energy, exact energy, minus the restricted Hartree-Fock energy, is actually called the correlation energy. Is that defined already? No. So this difference is called correlation energy. So correlation energy is the difference between the exact energy, or the Hartree-Fock minus the exact energy. That means when this 2 to 3% error that is there, that is the subject matter of electron correlation theory. So entire electron correlation theory would try to improve this 2 to 3% error, right? And would try to get you as exact as possible. So what we are going to discuss from now on is electron correlation. Why is it called electron correlation? If you think, what was the problem in Hartree-Fock? That we made an approximation of the two particle part, right? Because two particle part was not a separable one particle part, but we had to do a separation because we wanted a single determinant. And then two particle part was actually done by averaging. If you remember the Hartree-Fock, a Coulomb and an exchange Fock operators and averaging. But that is not the true two particle part. So that correlation is an English word. It just means the relation between the two particles was not taken care in the Hartree-Fock properly. And that led to this 2 to 3% error. So electron correlation is going to include this 2 to 3% error and is going to make the methods more accurate. Is it clear? So the theories that we are going to describe are all electron correlation theories.
Sir?
Yes.
So this exact energy we are taking from experimental values, or
Yes, you can take from experimental value. I will tell you theoretically which is exact little later.
Okay.
So theoretically, what is exact depends on what basis set you are using. So the exact in this case, theoretical exact is what I will call it complete full CI. As you do full CI, you will realize full CI in whatever basis you are doing. So if you want really exact, the full CI is exact. This basis has to be infinity. Then it's an experimental exact. But very often our basis is not exact.
Sir, here,
Basis
but
cannot
in
be infinite.
CI we also change the determinants, huh?
CI you also do?
Means we take multiple determinants, no?
Yes. So I will come to that. Determinant, but not one determinant. So if you take full configuration interaction, it can be potentially exact. Okay, if your basis is also very large. So in a complete basis set full, so that becomes your benchmark, theoretical benchmark. So if you are doing 61G calculation, then whatever full CI in 61G, that is my benchmark for all other correlation theories. So I will come to that. Huh? Okay. Then there are certain the problem of difference energy is also reflected in a very simple thing that we teach, that is hydrogen molecule potential energy surface. So this is the potential of the hydrogen molecule with the distance between the hydrogen and hydrogen. What you should get is something like this. So this is basically exact. Whereas this distance, this energy is hydrogen plus hydrogen, this curve. So what it means that at a short range, if I bring the two hydrogen atoms very close, because of the nuclear repulsion, they become very high, infinity. Then it comes down at some distance, which is where the hydrogen molecule is actually stable. It becomes minimum, and then the energy goes up, and it asymptotically reaches the two hydrogen atoms, sum of the two hydrogen atom energy, because at R equal to infinity, H2 at R equal to infinity, it becomes hydrogen plus hydrogen. Right? Because they are separated, correct? So this is my hydrogen plus hydrogen energy. So at a large distance, it should separate. This is the exact result. Now, if you look at the RHF, I don't know if it is done. It is something like this. So this black curve is the RHF. Now you can see it's unimportant that this is not matching. Okay, the energies can be higher, lower, okay, whatever. So at any given distance, energy is slightly higher, which is what you expect because of the variation method. Then exact compared to exact RHF is higher. So even here RHF is higher. But what is more dangerous that it just crosses the curve and becomes at the large distance, it does not separate into hydrogen plus hydrogen. It actually goes somewhere else. In fact, this energy is actually the H plus, H minus. So it separates into not two hydrogen atoms, but proton and a hydrogen. This is exact. So hydrogen at R tends to infinity for RHF actually goes to H plus H minus. And that is higher than H plus H. So H plus H energy is of course higher than H plus H. I hope that all of you understand. Can somebody explain to me why? Without doing anything, theory. Simple experiment. Why is the energy in gas phase? Proton plus hydride is lower, is, sorry. This is lower. Less than. That this is higher than the hydrogen plus hydrogen. Can somebody explain to me? So as you can see here, this is lower than this. Simple chemistry explanation I ask you. In fact, not only hydrogen, any A and B diatomic molecule in gas phase always separate Yeah, I'm sorry, I don't know why I lost it. Let me share this screen. Am I audible now?
Yes, sir.
I don't know why I lost the connection. So, can this screen be seen?
Yes, sir.
Okay. So, I don't know where I lost you. Did you hear this about this particular curve?
Up to say H plus and minus greater than.
Yeah, that's fine. So I was asking why hydrogen plus hydrogen is less than H plus H minus. It's actually not greater, it's less. So I corrected it. Can you tell me in gas phase when hydrogen molecule separates, it will separate the ground state. Ground state will be separating into hydrogen plus hydrogen, and not proton plus hydride. Or for that matter, any diatomic molecule will separate A plus B, including sodium chloride. It will be Na plus Cl and not Na plus Cl minus. So can you tell me some chemist explanation?
I think ground state is more stable.
Ground state of what?
Both A and B. I mean,
Yeah, A and B. So that's what I'm asking you. That the energy of A plus B, let's say A is more electropositive compared to B. This is still less than A plus B minus.
because E A plus is greater than E A and E B minus is greater than E B.
Why EB minus can be less than EB if it's electronegative? You understand my question? Sodium chloride.
Then there will be repulsive force between EB molecules.
There's no molecule here. Both are separated. I'm comparing between two systems. AB going to A plus B. And another is AB going to A plus B minus, where A is more electropositive than B. So I'm comparing these two on the right hand side. I hope you understand. So you have a sodium plus, chlorine minus, and you have sodium and chlorine. That also, so it's just sum. So you said this energy is higher than this energy. Fine. Why? Because every atom ionization potential is positive. Correct? So it requires energy to ionize. But what about this? Chlorine minus can be less than chlorine because you know it's electronegative. Do you understand my point? Hello?
Yes, but this difference will be higher.
Yes. So the point is that any ionization potential, that means even if an atom has the lowest ionization potential, is greater than any electron affinity. Do you understand? Of an atom. I'm talking of only atoms in periodic table. So for example, if you take cesium, cesium is the easiest to ionize. What does it mean? It has the lowest ionization potential. So very quickly you can ionize. And you take, let's say, fluorine or chlorine, which has the maximum electron affinity. Even then, the energy required to ionize cesium is higher than whatever energy you will get from going from F to F minus. You understand? So in the balance, this is always a larger energy. Hence, any A plus B minus is larger than A plus B. So when I'm doing the ground state, this goes to H plus H minus, which is larger. So in any case, the point that I'm trying to say that the RHF is qualitatively wrong. It is not even able to dissociate a hydrogen molecule. Forget about anything else. It's such a simple molecule, it cannot dissociate. Whereas we are more interested, whatever we have been taught is actually in this region, near the equilibrium distance. In this region, there is only an error, but qualitatively it is correct. I mean, the exact distance will not be reported, but when you look at the dissociation, RHF gives completely wrong result. So this is another deficiency which is manifested from the same reason, because at this region, what we are talking of is actually a difference energy. So in any sense, it is the difference energy which does not come out in the Hartree Fock. Now, this particular error fortunately can be cancelled within Hartree Fock, but going from RHF to UHF. Because it is known, here the problem is somewhat different. Because it's a 2-electron pair, when it goes to the atomic system, the 2 electrons go over to one of the hydrogen atoms. So it gives you proton and hydride, which is a wrong thing, because the electrons are spin paired in the RHF. So as soon as you make UHF, this will give reasonably good result, but not in all cases. This is a very special case which UHF can actually solve. So in all other cases, we need general theories for electron correlation. So we want to first analyze what would be the form of the exact wave function. I don't know if it is already taught, which is basically the full CI. So somebody asked me the question, what is exact wave function? So then I will get exact energy. What is the form? First I want to know the form. In actual calculation, basis set will also come in. But let me first look at orbitals and look at a form. So let's say that I have a basis which is exact. Basis of one particle. Or rather spin orbitals, which is exact or near exact. Of m dimension. So m is very large. Now we don't have to bother because we really can't. You know, in basis set that actually if you want to get exact, then it has to be infinity. We can't work with infinity, but it's a large enough basis. So this is not the point. But within this basis of one particle orbitals, what is the form of the exact wave function? So that is what I'm going to analyze. So to the analysis, let me do a 2-electron problem. If you remember Hartree Fock, what does it do? It takes up 2 spin orbitals out of the M and forms a determinant. 2 best spin orbitals, which is obtained by the Hartree Fock equation, right? So for hydrogen, it is sigma g alpha, sigma g beta. But I'm looking at the form of the exact wave function. So how do form the exact wave function for a 2-particle problem? Let me convert this into a 1-particle problem by keeping one of the coordinate fixed. So let's look at psi 1, 2 as a function of coordinate 2 for a given values of the coordinates 1. So let's say that it's a function which where R1, R2 changes, right? I'm just looking at it as a, well, spin coordinate as well as space coordinate, both changes. So I'm looking at it as a function where only this coordinate 2 is changing and coordinate 1 is fixed. In which case, I can use the mathematics and say that I can expand these as a complete set, and this M is a near exact or complete set. So this is a complete set, I can say, of functions which are, so let me call this some spin orbital function. Let's say chi I. So I think we have used chi for the spin orbitals. So chi I of 2, and then some coefficient which I will write, let's say Cji. So this is my psi jth function. I have several functions. So the jth function I'm writing as a linear combination of a basis. This is, I'm now looking at function which is coordinate 2 for a given value of coordinate 1. So this is going to be a function of chi I 2, and this is exact because this is a complete basis. So M is a complete basis. So in mathematics, you know, I can always expand one function in the complete basis of another function. So this is exact, no problem. What does the electron coordinate 1 come in? Electron coordinate 1 will dictate this coefficient. So the Cji, if I change the coordinate 1, next time, what will happen? The form will still be the same, but these values will become different. So the Cji will change as coordinate 1 changes. So it is a function of the electron coordinate 1. So look at it how I'm doing it. I'm looking at the 2 electron function as a function of only 1 electron, keeping the rest of the electron or electrons as a parameters. So they are given, they have a set values. So my coefficient will now depend on those parameters. Okay? Then I can immediately say that this Cji is also a function of electron coordinate 1. So I can write Cji1 in the same m-dimensional basis as some d of chi j. J or I can expand in k, whatever, k equal to 1 to n. So it will be d kji, whatever, it doesn't matter how I do it. The point is, if I now multiply, this will become a product of all chi j, chi I, etc. If I do n dimensional, so that for 2 dimensional I can write psi 1 2 will then become sum over j, sum over I, Cji, chi j 1, chi I 2. Actually, one simpler way is that you don't write this j here, you let it remain like Ci, and then expand Ci as a function of 1 with a sum over j. So that will also do. So I'll rewrite this whole equation again. Okay. So what I wanted to write is the following. So psi 1 2, you don't care which state it is, that can come later, is sum over I equal to 1 to m Ci chi I of 1. But then now Ci is a function of 1. So this I can write as sum over j dji or dij chi j of 2. Chi j of, sorry, this is chi I of 2, this is chi j of 1. So I have first considered this as function of coordinate 2. Then these are parametrically dependent on coordinate 1. So I can write this in this following manner. So if I put this here, my psi 1 2 then becomes a double summation over j and I. So j is also 1 to n. Double summation over j and I, and dji chi j of 1 chi I of 2. Is it clear? So basically, I am doing this expansion in terms of one electron, then this I am expanding again by another dummy index. So of course, already one dummy index is there, which is this I. So I have to bring in another j and continue like this. Please tell me if there is any question here. So basically what I'm trying to say, that I can write this in this manner. Okay, instead of C, I just wrote D. So you can cut this out. You start from here. Huh? So first I've considered this as electron function of coordinate 2. Then the coefficient must depend on coordinate 1. So this coefficient is also written as an expansion of chi j. Now I have to use a different dummy variable. So then psi 1, 2 becomes summation over these two dummy variables. And this becomes exact. Because M is complete, so this becomes an exact function. If you look at this, of course, it's a simple product. I know that a simple product is not acceptable. So everywhere there is a product, I transform this to a determinant. That's all I will do. So then my psi 1, 2 will become sum over j, sum over I, each of them over m, dji, and a determinant of chi j, chi I. I hope all of you are familiar with this notation. So only I can make this determinant within I and j. So immediately you can see my 2 electron wave function is not one determinant, but sum over all these determinants. Because there is a relation between j and I know that chi j cannot be equal to chi I, now that I have made it a determinant, and j greater than I and j less than I are actually identical with a phase factor. This can be written as simply j less than I dji chi j chi I. Because they are not linearly dependent. So chi j chi I and chi I chi j. I hope all of you know that this is negative of this, right? So they are linearly dependent. So I don't need to take all. I can take only j less than I, j greater than I need not take. And of course, j equal to I will be 0 because it's a determinant. So you can clearly see that in an m-dimensional basis, the exact function does not have one determinant, but how many determinants? Can somebody tell me now? How many determinants the exact function has?
M into m minus 1. No, sorry.
Right. M into, no, MC2. M into m minus 1 divided by 2. Is it clear? Because I'm taking only one product, j less than I and not j greater than I. Because the diagonal is not there, from m square I subtract m. But I'm taking only half of them, so it is m into m minus 1 by 2, which is MC2. So MC2 number of determinants, and that is all possible determinants in this m orbital space. If I take, then only it will be exact in a complete set. Whereas in Hartree-Fock, I don't have that. I have only n electrons, n spin orbitals. So it is hopelessly bad. This kind of mixing of determinants or what I call linear combination to form wave function is called configuration interaction. Or CI. So you can see that the wave function truly is a linear combination of many determinants. So this is the interaction. What is configuration? Configurations are determinants. They are interacting with each other to form the wave function. If I take all m-dimensional bases, it is exact. But even within this, I can make lots of approximations. So you will see. So if you take all determinants in m-dimensional basis, then I can say that the wave function is a complete CI or full CI in these bases. Of course, somebody asked me, is it experimentally exact? Still not until this M is exact. M can be exact only if it is very, very large. So it depends on what is your M. So that is where the basis set will become very, very important to answer that question. So there are 2 points. One is the theory itself. Hartree-Fock is not good. Second is basis set. Basis set you have to keep improving, but the theory also you have to improve. So what we are discussing first is the theory, because if you just improve the basis set and not the theory, you will only reach some limit of which is still hopeless, right? So we need to improve the theory, and that is what we are trying to do. So full CI is all determinants. If on the other hand, if you take a partial number of sets of determinants, then this will be incomplete CI. Incomplete, or sometimes you can call truncated CI. And this can still better than the Hartree-Fock. It is still better than the Hartree-Fock. Because Hartree-Fock takes only one determinant. So if I include that one determinant plus anything else, it will always improve. That's a variation method. So it's very important to realize that the CI, where I do a mixing of determinants to form a function, is a method which is better than the Hartree-Fock. Now, if you take all the determinants, in this case it is MC2, it's an exact wave function in that basis, or a complete CI. Any partial set that you take will make it incomplete or truncated CI. Okay, I have paraphrased this with only 2 electrons. You can very easily see that you can expand this to n electrons, right? So n electron wave function will then become a linear combination of MCN determinants. Is it clear? Because it's an electron, so instead of MC2, it will become MCN. How many ways you can form determinants out of M bases, n electron determinants? So that is picking, it's like a combination problem in mathematics, picking up n out of m. So that's your MCN. Is it clear? And we will see how to categorize the determinants. And then what Hartree-Fock does is to calculate these coefficients, because now all that is my unknown parameters is these coefficients, because the basis is known. Okay, so it calculates these coefficients by a variation method. Unlike Hartree-Fock, where variation was done for the orbitals, here variations are done only for this linear combination coefficients. So this particular variation has a special name, and it is called linear variation. Has this been taught, linear variation? Where you only find out the linear combination coefficients and the functions are frozen. Whereas in Hartree-Fock, it was very different. You are actually looking at the orbitals, which is not a linear variation, because orbitals have exponential. and you're looking at those coefficients, right? So it was much more complex variation, but here it's a much simpler variation called the linear variation. I just want to know whether linear variation has been taught or not. Then I will teach that first. I think I taught variation method, I remember, but I don't remember if I taught linear variation or madam has taught. That's what I wanted to know. Can somebody answer?
I think not.
Not. Okay. Okay. So because this procedure will require linear variation, at some point of time I have to teach linear variation, maybe tomorrow or maybe in the next class. So my classes will continue. I just want to refresh myself that in the next class I'm going to first do categorizing the determinants. So for an n electron problem, how do you categorize the MCN determinant? That's the first thing that I'll do. Okay, so you'll see what I mean by category, and then to apply linear variation. And that will essentially give you CI equations. And then we will look at incomplete CI, and that is very important, because even you can very easily see you cannot do a complete CI, because if M is very large, it's a factorial problem. So number of determinants become too large, so you still have to truncate. It is better than Hartree-Fock result, but there are certain problems. What are the problems of incomplete CI? So this is a very, very physical problem, what we call the problem of size consistency, dissociation problem, which I discussed in the RHF, hydrogen plus hydrogen. It will come back in a different way. And that actually will make CI very unsuitable today. So most of the many body theories don't use CI as the electron correlation problem, but it's very important to learn. So we would use actually perturbation theory, or more glorified method today is what is called the coupled cluster method. So we'll come to that later, but let us go systematically. So tomorrow's class, I'm going to start with categorizing determinants. Time permitting, we'll do linear variation, and then we'll go one by one. So Monday I have full 2 classes, and tomorrow what time can you refresh? 3 p.m.
Yes.
Yeah. Okay. So I will close today. So I'll start at 3 p.m. But once again, I just wanted to tell the basic idea of a CI is a linear combination of determinants, and the way it is derived is in the following manner. I gave an example of a 2-electron function. First, look at it as a function of coordinate 2 for a given value of the coordinate 1 or whatever, n minus 1. So in this case, the coefficient, I just cut this here, come here. The coefficient becomes function of 1. That can be further expanded as a function of 1. This is function of 2. So if you match this here, it becomes dji, chi j of 1, chi I of 2. And then you replace the product by determinant. So it's basically a linear combination of determinants. And there you need not take all ij. You can take only j less than I. So it is MC2 number of determinants. So this mixing of determinants to form a function is actually called a configuration interaction. And all determinants in an m-dimensional basis, if I take, then it is called complete basis, complete CI. If you take partial, then it is called truncated CI. And very often we are forced to do truncated CI because MCN is still very large. And I think you can very easily see, if I have 10 electron problem like water, and your basis is just 100, which is very good basis, of course, you can see what is 100 C10. I think all of you can do this exercise very easily. It's 100 factorial by 10 factorial, 90 factorial. Even if 90 factorial cancels, you'll have 91 into 92 up to 100 divided by 10 factorial. Please do this calculation. By any calculator, if you do this calculation, it will be mind-bogglingly large. So it will be very, very difficult to do full CI, unless it's a very small systems. So we will be forced to do truncated CI. In that case, we also need to know what are the problems of truncated CI. Okay, and then we will go to the perturbation theory and so on. All right, so tomorrow we'll see at 3 p.m. So we have basically started electron correlation. So electron correlation theory is basically going beyond Hartree-Fock. After I do CI, I will also discuss certain features of electron correlation. After I complete this, even before we go to perturbation theory, certain qualitative features which I deferred deliberately at this point. We'll do certain features of electron correlation and then go to the perturbation theory. Okay? All right. So I think we'll meet at 3 p.m. tomorrow to continue the CI. Is there any question? Otherwise, I'll stop. Okay, then I'll stop. Yeah. So if there are any question, you can still ask me. I'm on the screen. All right. So if there is no more question, then we'll meet at 3 o'clock tomorrow. Okay. All right. Bye.